So for number two, we have to determine the order of the reaction in respect to the reactants. And then we have to write the rate law. Now, because of time constraint, I'm not going to show all the work. I'm just going to scribble right here. I'm going to consider experiments 1 and 2 to tell the order of OH minus. I can see that when it doubles, the rate also doubles. So I would say that the OH minus would have the first order. And then for the other reaction, I would consider reaction 1 and 3. I mean, experiment 1 and 3. I can see that when the COO2 concentration doubles, the rate quadruples.
Second order.
So second order it is. So I can find the rate law. Okay, 0.166 to 0.661. That's a multiple of 4. There's a multiplication of 4. Now, and I'm going to skip part B and part C for the moment because that's pretty straightforward. Now, I want to look at part D. Take a look at part D. Okay, so they're not telling you which one's a slow step. So you've got to determine which one is a slow step, which one is the rate determining step. And you have to show that this mechanism is consistent with both the rate law for the reaction and overall stoichiometry. All right, now this is the harder part. Now, let me break this down a little bit more. Not only you have to find out the rate determining step. Something's going on right here.
Oh, it's equilibrium. No, it's a reversible reaction.
Both are correct, and there's something about this in the moment. Okay, so now how do we tell the? Now remember how we said we determined the rates law from the rate determining step.
Yes.
So we are looking at the reactions, the elementary steps, and we say, hey, which one would give you the rate law that it's written above? And when you look at it, the answer would be none of them.
Because in the first one, OH is in a reactant.
Correct.
And the second one,
CO2 is not there.
yeah. And the
Third one, CO2 is not there. So how would you figure out? Now, so I want to give you a pretty abbreviated way of explaining this. Okay, now this is not technically correct, but for the sake of doing this math, this calculation, I'm going to say it. I'm going to say that when you look at this equilibrium sign, feel free to you can look at it as an equal sign.
Oh, so that means that ClO2 equals Cl2O4. So in the second equation, you can put ClO2.
So that's how you view it, but how do you actually write it? So this is the slow step. So you would say the rate is equal to K, Cl2O4 times OH minus. Now, here's another thing too. We have a name for Cl2O4. This little thing right there, it's called an intermediate. It's something that is made in the process of the reaction and then being consumed in the reaction. So that's why we call it intermediate. And we cannot show an intermediate in the rate law because nobody knows there's an intermediate because it doesn't show in the reaction. So what do we need to do? We say, oh yeah, we would need to express the intermediate with the replacement of the reactants. Well, how? what is the definition of equilibrium?
Both sides are equal, right? And also the reverse, like the reaction can go both ways from product to reactant.
Yes, but that's not the meat of the definition. Nope, that's actually the wrong direction. When we say equilibrium, and we will talk a lot more about equilibrium later on, is that the rate forward is equal to the rate backward. And we can write the rate law in this case. Now, the whole K thing is not something that you have to worry too much. So when we have K1 over K2, let's just say K12, it's equal to ClO2 square. It's equal to Cl2O4, and then you can replace it over here. So K times K12, ClO2 square, and then OH minus, and all the K's will multiply together to become another K. So doesn't matter. And that's how you show that the rate law is consistent with the one that we found out earlier from the experiments. And that is also consistent with the stoichiometry because we have 2 ClO2 plus, we have ClO2 and the OH minus in the reactants, okay? And again, this is the overall reaction. You should not use the coefficient to tell the exponent unless it is an elementary step or the step in the reactions. So now that is something that you want to practice more because you are destined.
This is going to be bad for you.
It would have to be some variations of this. No, it's not hard compared to what you would see in the second semester.
Because this is like the first new stuff. We can't rely on majority of the